Swayam Prabha. Digital India. Educated India.
Hello, welcome to the course on comprehensive view of speech processing. So, this is lecture number 21 in this course. So, today we are going to discuss the continuation of the linear prediction analysis of speech, which we started from the last two lectures. And so, in the last lecture we discussed about the error analysis under the linear prediction modeling of a speech. So, where we observed that as the prediction order increases, the error will be reducing, and when the prediction order equals to 0, you can able to observe the maximum error. So, that is obvious, because since we do not have any knowledge about the past history, so obviously the guess or the prediction will be purely random. So, the error that will be encountered will be maximum, and afterwards, by knowing the past history or the preceding samples, if you increase the number, if you know the more and more preceding samples, so with that you can able to predict better, because idea is that since the samples are correlated, so by having knowledge of more previous samples, we can learn the correlation. So with that we can able to predict the present sample in a better way with the help of the previous samples more. So that you can able to observe here in this plot. There are a solid curve and the plot with the dashes. The solid curve indicates if you take a voice to speech segment, and if you perform the error analysis for different orders of P, for different orders of the linear prediction analysis, you can able to see when the prediction, when the 0 the past history equals to 0, then the maximum error, and afterwards immediately the error will be reduces as the P increases. And whereas in case of unvoiced speech also you can see the trend, but the decrement in the error with the unvoiced speech will be less compared to the voiced speech. So, this is evident because in case of unvoiced speech, the speech signal appears to be like a random, and the samples are not much correlated. So, because of that, even though if you increase the prediction order, the error will be come down, but there is a drastic difference between the error magnitude for a voiced speech segment versus unvoiced speech segment. And similarly, we have also analyzed the voiced segments, voiced speech segments for in the both LP using LP analysis, where we observe that what will be the error signal that you can able to observe in case of voiced speech. And in the error signal, what we observe over here is that if it is a voiced speech, then you can able to see the maximum error at the instance of glottal closure. At the instance of glottal closure, because at the instance of glottal closure, the excitation signal will generate a narrow pulse, almost like impulse kind of a thing. So, since the impulse will be a sudden change in the signal amplitude in a very short interval, so you cannot predict that. That's the reason that when you try to predict with the previous samples, so the occurrence of impulse or the presence of impulse is not predicted by the linear prediction analysis. That results to be the error. So, that way in case of voiced speech, you can able to see a peak error at the instance of glottal closure and at the same time at the beginning of a voiced segment also. Suppose we are starting the prediction at the beginning. So, since we are starting from the 0th sample, so we have no knowledge about the previous samples. So, therefore, obviously the error will be high, you can able to observe at the beginning of a segment. And we also analyzed the spectrum of a voiced speech segment by applying a Fourier transform, how the spectrum looks like. And for the same voiced speech segment, if you perform in the LP analysis by using LP synthesis filter, so where it is nothing but all pole filter, the approximation of that. So, if you analyze the filter response of the all pole filter is nothing but the response of a vocal tract system. So, if you analyze the spectrum of, or you can say that the spectral characteristics of the vocal tract filter, where it is appears to be like the smooth spectral envelope almost coincides, almost very close to the speech spectrum. And the difference between the LP spectrum and the speech spectrum will be the spectral envelopes are both are almost very close, but the only difference is that in case of speech spectrum you can able to observe the ripples, and these ripples are due to the periodic excitation. And similarly, if you analyze the spectrum for the error signal, you can able to see that the error signal response, the frequency response will be almost flat, and where you can able to observe the ripples. So, these ripples are because of the excitation, because of the periodic excitation. So, the same thing you can able to observe with another vowel also, a similar observation you can able to see. And now, if we move on to the other vowels, you can see here it is listed, there are about the vowel signals corresponds to the 6 different vowels, right. And here you can able to observe here for some vowels where you can able to see the noise is superimposed on it, and you can see for the top 2 plots and the bottom plot where you can able to see the noise also overimposed on that. But on top of it, across all the plots, here you can see there is a periodicity, exists a periodicity, right. And for some plots where the signal will be appears to be like a smoother one, whereas other plots where there is a periodic signal, but on top of that one there is some aperiodic component is also present, superimposed on that. So, that is observed, that is the signal the vowel segments in the time domain you can able to observe it. For all these vowel segments, if you perform the linear prediction analysis, and in that linear prediction analysis, if you observe the prediction error, you can able to see the prediction error plots, the prediction error signals corresponds to these signals are observed to be like here. And here you can see for the sake of display purpose, here the prediction errors also has to be zoomed with respect to the signal. So, otherwise the prediction error magnitudes are very small compared to the signal amplitude, that we have seen, we observed in the previous lecture also. If you look at here, the signal amplitude varies from almost like minus 7,000 to the 4,000 plus 4,000, that means this range is about 11,000 or 12,000, whereas if you look at the error signal, the range is from minus 1300 to like about 1000 kind of a thing. It means it is about 2000 altogether, and whereas here the range is about 11,000. So, and but here for the purpose of display, where these prediction error signals also will be zoomed up at the same level of the signal, right. So, the thing that need to be observed over here is that with respect to the signal, you can see the error, prediction error, where you can able to see that in all the prediction error plots, where you can able to see the maximum error at a particular location, and you can able to see this maximum error will be observed at a periodic intervals. So, this is because, as we have mentioned, that since all these are the vowel segments, so these vowel segments are produced due to the vocal folds vibration, and these vowel segment, for all these vowel segments, the excitation will be the vocal folds vibration or vocal folds through the vocal fold excitation, vocal folds vibration. That means here whenever the vocal folds starts closing, it generates a narrow pulse impulse kind of a thing, and that cannot be predictable. So, because of that, at a glottal closure locations you can able to observe the maximum error, and the same observation more or less can be observed across all the vowel segments. But there are other places where there will be noise at other parts of the signal also, but otherwise the common observation over here will be in case of voiced segments. If you analyze the error signal observed to be, you can able to see at a periodic intervals the maximum error can be observed, the peak error is observed at the periodic intervals. So, and this error as we are seeing, both the linear prediction for the purpose of synthesis of a speech and a linear prediction for the purpose of analysis, in both the cases we have seen, and we observed that the analysis model and synthesis model are like reciprocal to each other, where in the synthesis model, if you look at the speech, the system transfer function will be 1 over A of Z, it is all pole system, whereas in the analysis model, what you observed is that the system transfer function will be simply all Euro system A of Z. It means that the system response will be exactly inverse to each other and all. So, that is the reason that here if you see these error signals are also nothing but they are you can use these are the excitation signals to the corresponding speech segments, excitation signals to the corresponding speech segments, because from the speech signal it predicted the prediction filter or the predicts everything in the LP analysis, but this is the leftover. this is not able to predict. So, that is the reason that it will be emerged as error. So, these error signals are also known to be linear prediction residual, because in the process of linear prediction, while you are modeling the speech using the linear prediction analysis, so this signal, the error, means nothing but this is not predicted, because this is the difference that you observed between the actual signal versus the predicted signal. So, therefore, we can view this is also can be viewed as a linear prediction residual signal. It means that in the process of linear prediction analysis, so this this particular signal is observed to be not predictable. So, therefore, you can view it as the residual signal. That means, after prediction, whatever is left over, that is known to be the residual signal, and this residual signal is a part of the derived from the linear prediction analysis. So, therefore, these are known to be linear prediction residual signals, and these are also can be viewed as excitation signals, are also known to be error signals in the prediction process. So, now we try to analyze what is the effect of the prediction order on the signal spectrum when you are capturing the signal spectrum, or when you are trying to capture the characteristics of a speech signal using a vocal tract filter, like with a prediction coefficient. So, what is its effect, the spectral properties that are captured by the prediction coefficients, like what are its effect, what is its impact on the order of the prediction. So, that the same thing we analyzed in the case of error, right. So, when you are analyzing the error in the prediction with respect to prediction order, as we have seen that as you increase the prediction order, it is nothing but if you depend more, if you perform the analysis with more and more history, prediction P is more, then obviously the error will be reduces, error will be coming down, because as you are taking more and more previous sample for prediction of the present sample, you can able to see that the error will be gradually reduces. Maybe initially the error will be drastically reduces at a very rapid phase, but afterwards there will be still the error will be reduced, but the decrement trend will be slightly slower, the slope is very low. So, therefore, it slowly reduces after a certain the prediction order, but as you increase the prediction order, the observation is that the error will be reduced, there is a decrement in the error that will be observed over here. And now, the same way here we will try to analyze that. So, what is the impact, what is the effect of the prediction order, right, or the number of prediction samples when you are estimating the spectral envelope of a vocal tract filter, right. So, for that here if in this plot, if you look at here, so the top plot is nothing but had taken a vowel segment, we have taken the vowel segment, because here we have considered the vowel segment because when you are uttering the vowel segment, the vocal tract will be opened widely, and where you can able to see a proper the formant frequencies or the resonances. You can see clearly the 3 or 4 resonant frequencies are also known to be formants, where the dominant frequencies in the spectrum. So, that you can clearly observe in case of the vowel utterances. So, that is the reason that here when you are analyzing the spectral envelope that will be captured by the linear prediction analysis. So, for that purpose here, for the analysis purpose, we considered the vowel segment, and here we had taken as around 20 milliseconds of vowel segment. It means around 120 samples were considered. You can see 0 to 119, around 120 samples, and so here for this particular vowel segment. So, if you compute the spectrum using the FFT normal fast Fourier transform, where you can able to see the spectrum will be this one, and here this spectrum is corresponds to this particular speech signal. Here the speech signal is a voiced segment or the vowel segment, like, and for this vowel segment, if you compute the fast Fourier transform with a certain size of n, you can able to see that the spectrum is like this. So, from this spectrum, what you can able to observe here is that there are a kind of peaks over here at a gross level, I am saying here, and then maybe over here, right. So, the formant frequencies may be here, here and here it may be, right, and but from this spectral envelope, it will be difficult to bit difficult to compute the formant frequencies or determine the formant frequencies, because here this in this spectrum along with the vocal tract, the spectral envelope of a vocal tract, the spectral characteristics of the excitation is also superimposed on this. So therefore, if you look at the entire spectrum, where it is like the harmonics of the pitch, or the harmonics corresponds to the periodicity of the excitation, is also superimposed. So therefore, here from this spectral envelope of the fast Fourier transform, detecting the form and frequencies will be somewhat ambiguous. Suppose if you try to hear, so it will be like a bit ambiguous, like whether you have to pick this peak or this one, because there are the ripples over here, right? And so because of the presence of ripples superimposed on the spectral envelope of a vocal tract shape, so there will be ambiguity in detecting the form and frequencies and all, right? So but this is the true spectrum. This is the true spectrum of the speech segment corresponds to this vowel segment. And whereas if you perform the linear prediction analysis on this speech signal, and from this linear prediction analysis we can here performing linear prediction analysis is nothing but we know this speech segment, right? And from this speech segment we will try to compute the linear prediction coefficients corresponds to this particular the speech segment or this particular speech frame, right? So how do you do that? So we know the speech signal, and then using by performing the autocorrelation analysis, you will get the autocorrelation coefficients corresponds to R of 0, R of 1, R of 2 up to R of p, right? That depending upon the prediction order, right? So once you have autocorrelation coefficients, then you can plug in these autocorrelation coefficients into that equation, whatever the expression what we observed, ak summation of ak into R of I minus k equals to like R of 0, right? That is the expression. And if you solve that the matrix relation using the Durbin's relation, the Durbin's recursion, you can able to get the AKs, like the optimal AKs, right? Because we got that relation by taking a first order derivative of the error with respect to each of the prediction coefficient, and then by solving those equations you will get the AKs. So that way for a given speech frame you can able to compute the AKs. Again, the number of AKs that depending upon the prediction order we have chosen, right? So that way you can able to compute the prediction coefficients, and once you compute the prediction coefficients, then we know that the vocal tract filter is nothing but the all pole filter 1 by A of z, right? And then from that you can able to compute the all pole filter response, and that all pole filter response is nothing but the vocal tract system response approximated by or modeled by the LP analysis. So with that, if you compute the LP analysis, right, by order p, when the p equals to 4, like when you choose p equals to 4, it means for prediction of a samples signal, we consider the past 4 samples. If you consider the past 4 samples, then you can able to see that with that if you design an all pole filter, the all pole filter is nothing but now here p equals to 4 means you will get the all pole filter with the order 4, that means 1 by A of z, where the z polynomial of order 4, right? So by solving the with that z polynomial of 4, if you analyze the response of that particular system, right, 1 by A of z, where the denominator polynomial of order 4, if you try to analyze the spectral characteristics of that particular system, right, you can able to see that the spectrum will be observed to be like this. The spectrum is observed to be like this. Here you can see this particular spectrum, LP spectrum for the order p, you can able to see that the characteristic will be something like that. It is like at a gross level you can able to see this one, because here this is the true spectrum. You can see the true spectrum at a initial, that means like for example this is a maximum 3000 hertz, 300 hertz, it means up to 1200 or 1500 the spectral envelope or the spectral the frequencies having higher energy, and afterwards the energy will be low, right? So the similar thing at a very gross level, if you use the prediction order 4, the LP spectrum, that the spectral characteristics that were captured for the vocal tract filter with the p equals to 4 will be something like this, right? This is approximate version, because we have considered only p equals to 4, right? With the p equals to 4 we can able to see the spectrum will be something like that. And then if you increase the order of prediction, when you say p equals to 8, if we choose p equals to 8, it means we are considering the past 8 samples, right? So therefore, then we will get here when you perform the analysis, LP analysis with p equals to 8, we will get 8 coefficients, and then if you plug in that 8 coefficients into the vocal tract filter of 1 by a of z, so you have a polynomial of order 8. So with the polynomial of order 8, and if you compute the response, the frequency response of that, you can able to see the LP spectrum with 8 LP coefficients. You can see the spectrum will be something like this. And now if you look at this particular spectrum, this is almost like very close to the true spectrum. This is the true spectrum where it has a ripples, and it also contains the vocal tract characteristic. The overall envelope, the gross envelope of this is nothing but is approximation of vocal tract system, and then the ripples that are present over it, those are in view of the excitation signal. And if you look at a gross envelope of this one, this is almost close to this one, right, when the p equals to 8. And if you increase the order for the p equals to 12, still you can able to see the LP spectrum corresponds to p equals to 12 will be this almost follows the same thing. This is almost very close, but here at a p equals to 8 to p equals to 12, the high frequencies will be better resolved here. You can see at the high frequencies here you can able to see only one peak, whereas here you can see almost like this one. And when you increase the p further, you can see that there are like the other places also you can able to see here, even this also captured, right, and even here also this particular envelope is also properly captured. So that way when you go p equals to 16, it is captured. But here in view of analysis of a speech, we don't want all these frequencies, right. We want only the 3 or 4 dominant frequencies, and that can able to discriminate the sounds that are produced by the speech production system, right. And if you increase the p further, like if you take a p equals to 20, right, you can able to see like more peaks, right, and this is because as you increase the order of prediction, right, so you have a polynomial of order 20. So with the polynomial of order 20, there are like if you try to analyze the roots of this polynomial, there are many possible complex conjugate pairs used to be there. Like for every complex conjugate pair, you have a pole, right, you have a pole, you have a corresponding formant frequency, right. So if you have a p equals to 20, means like you have a maximum possibility of 10 pairs of complex conjugate pairs can be observed over here. So all these 10 will try to show the peaks, will try to show its presence in the spectral envelope. So that way in this case the spectral envelope is observed to be like there more spurious peaks are observed in the spectral envelope. More spurious peaks means here the overall spectral envelope resembles like this, but we don't want all these the ripples. We want that the significant peaks which are corresponds to the dominant frequencies offered by the vocal tract system. So that you can clearly see when if it is n equals to when p equals to 8 or p equals to 12, you can able to see like unambiguously without any ambiguity, you can able to see that there are 2 peaks. Here there is a peak, here there is another peak, over here there is another peak here. In case of p equals to 12 also, roughly you can see a peak here, and then here there are 2 peaks, and then you can approximate, like take a middle of that or whatever it is. But in other cases here you can see there are more peaks. Here you have a peak, here, and again here, and so on. For p equals to 20 there are more. If you increase the p further, like p equals to 30, and you can able to see that like more more ripples you can able to observe here, and with that you have ambiguity in picking up the formant frequencies and all. So here the observation over here is that in view of capturing the spectral characteristics of a vocal tract system using the LP analysis, right, with the when at a lower order, if we choose the order p is very small, then the spectral characteristics that was captured by the filter will be very gross level, will be smoothed out, and you may not capture all the formant frequencies. You may that depending upon order p, because here the p equals to 4 means at max you can able to find, you can able to determine, you can able to get the 2 pairs of complex conjugates. 2 pairs of complex conjugates means only 2 poles you can able to present. The 2 pairs of poles, 2 complex conjugate pairs poles you can able to observe. So with that the spectral envelope contains maximum of 2 peaks. Whereas here you can see in this case, even though p equals to 4, you see only one peak. What it means? It means that here, even though the polynomial order equals to 4, out of that 4, only one pair of complex conjugate pairs, only complex poles exist, and the other two may be the real poles. Other two may be the real poles. So therefore, you can able to see only one peak in the response. Only one peak in the response. Similarly, in case of p equals to 8, also you can see only the 3 peaks. It means that even though the polynomial order equals to 8, you can able to see out of this polynomial of order 8, out of these 8 poles, 6 of them are the complex conjugate poles. Like 6 of them is 3 pairs of complex conjugate poles and a pair of real poles may be there, right. So that is the reason that if you choose order less, LP order very small, very less, right. So in that case, the spectrum that will be captured will be, right, the spectrum that will be captured is not the true spectrum and all. The spectrum that will be captured will be like, it will not capture all the formant frequencies. So the spectral envelope that is offered by the LP filter with a lower order will be not accurate, right. And at the same time, if you take a larger prediction order like p equals to 20, 25 or 30, in that case you will get the spectral envelope, and where the spectral envelope contains a lot of spurious peaks, and from these again it will be difficult to like figure it out, or difficult to determine the exact formant frequencies, because there are a lot of spurious peaks will be there, and then we have an ambiguity in determining the formant frequencies if you take order large like higher values of p. So therefore, the reasonable order p for capturing the like vocal tract proper the true vocal tract shape, or the approximate vocal tract shape close to the true envelope will be like, it varies from order of 8 to 15, order 8 to the 15, right, order 8 to 15. So the usually order 8 or 10 will be more reasonable to capture, because order 8 means you can get a minimum 3 formant frequencies, right, and order 10 will be you can get the 4 or 5, that depending upon the presence of complex conjugate poles here. So 8 to 12 will be the reasonable order with which you can able to capture the vocal tract shape almost like very accurately compared to the vocal tract, the spectral envelope offered by the true spectrum and all. So from this the observation over here is that if you increase the order, that means if you consider the very lower order for LP analysis, the spectral envelope or the spectral properties of the vocal tract system that will be captured by the LP model is not accurate. It will capture only the gross spectral envelope. With that, you miss some of the formant frequencies. And at the same time, if you take a very higher order, the lot of ripples or the spurious peaks are present, and with that the true dominant frequencies or the true formant frequencies capturing from that are will be difficult. So therefore, the reasonable order for the linear prediction analysis for in view of capturing the spectral envelope will be like, it is in between like 8 to 12 or 8 to 15, right. So whereas in the error analysis, what we observed is that as you increase the linear prediction analysis, the error will be reduced, and we have observed that the error will be drastically reduced up to, if you consider the order like 6, 7 and 8 and so on, afterwards the decrement in error or decrease in error is less, decrease in error will be less. So therefore, the reasonable order for performing the linear prediction analysis in case of the vowel segments will be like around 8 to 12, like 10 is decent enough in the via media. So the next thing is that we will try to discuss about the capsular analysis of a speech, and we have observed here like when you perform using linear prediction analysis, we can able to separate the vocal tract component and the excitation component, right. In the linear prediction analysis, what we observed is that if you, when you are performing the linear prediction analysis, it means given a speech signal, right, when you try to capture or when you try to find out the optimal LP coefficients for the given order, in that process the error signal whatever we observed, it is nothing but like the vocal tract, or you can say it is nothing but the excitation component of the given speech frame. It is nothing but the excitation component of the given speech frame, because the quotients whatever they capture, they mostly capture the characteristics of the vocal tract system. They mostly capture the characteristics of a vocal tract system. That is what we have observed, right? And whatever is not captured from the vocal tract system is represented as error signal. So, the error signal is nothing but can be viewed as, for a given speech signal, this error signal will be a kind of an excitation signal corresponds to the given speech frame. So, that way the prediction coefficient, the linear prediction coefficients, whatever is captured in the analysis phase, that represents the vocal tract system response, and whereas the error signal whatever is outcome of the linear prediction analysis can be viewed as the excitation signal and all. So, that way from a given speech signal you can able to capture the vocal tract response and as well as the excitation signal component of the speech frame and all, and you can use these two different components separately for performing the speech task in view of either speech recognition or a speaker identification or a language identification separately. That means you can able to take the error signal, and from the error signal itself you can able to, with the error signal itself you can able to derive some appropriate features, and you can able to analyze that for discrimination of sound units. Likewise, you have LP coefficients are there. From the LP coefficients also you can also derive the important features from that to discriminate the sound units, because we know that in case of LP analysis the prediction coefficients capture the LP spectrum or vocal tract spectrum, and in case of voice segments, as you see that for different vowels the formant frequencies are different. So, with that you can able to discriminate the at least the vowel segments and all the vowels to some extent. And likewise in case of excitation signal, so from the excitation signal also you can able to see the error, and the error behavior may be different for different vowels, that depending upon the way the vocal folds the vibrate for different sound units and all. And not only that, even the other articulator movement that also will be reflected as part of the excitation. So, if you look at here, there is another way of separating the vocal tract and the excitation signal, and that is known to be the capsule analysis. And here the way the capsule analysis will be carried out will be here it is presented over here. You can see here in a linear system viewpoint, we can view the speech signal S of t is nothing but the convolution of the excitation signal and the vocal tract system response. You can see the excitation signal is different for different sound units, because basically the excitation signal will be of three kinds, right? Voiced excitation, unvoiced excitation and mixed excitation, right? And there are three types of excitation. With that you can able to generate the different sound units, right? And also here the vocal tract system also, the shape of the vocal tract system dictates the sound unit, the characteristics of sound unit. So, the combination of the response of vocal tract system and the excitation signal characteristics, that leads to that provides you the speech signal, acoustic signal, which carries the sound specific information, and which in turn contains both the components of excitation as well as the vocal tract system and all. So, therefore, you can see the speech signal from this linear system perspective, like if you model the speech production as a linear system, right, as the outcome of linear system, then the speech signal can be modeled as S of t equals to excitation signal convolution with the vocal tract response. Here E of t and V of t, E of t corresponds to the excitation signal and V of t corresponds to the vocal tract system response. So, the convolution of these two is nothing but the S of t, right. And then in a frequency domain, the equivalence in the frequency domain is nothing but S of omega is nothing but the spectrum of a speech signal, right. If you compute a Fourier transform of S of t, you will get S of omega. Likewise, if you compute the Fourier transform of excitation signal, you will get E of omega. Likewise, for V of t, the Fourier transform will be V of omega. And in a spectral domain, S of omega is equals to the product of the spectra of the excitation and the spectrum of the vocal tract system, because this is we know, because here in the time domain the S of t is related to these two in a convolution between them. So, therefore, in a spectral domain, the corresponding convolution will be termed as a product of the spectra, the product of the associated spectra, right. So, S of omega equals to U omega into V of omega. So, therefore, whatever the S of omega you are observing, that means by computing f of t on S of t, you will get S of omega. So, this S of omega is nothing but a product of the excitation signal spectrum and the vocal tract response, the spectrum of the vocal tract and vocal tract system. So, E of omega and V of omega, and here from the spectral domain, if you want to separate these two, right, because they are product, because the result will be S of omega, which is a product of that one. So, you cannot separate directly, and that too these signals are like complex signals. So, in that it contains both magnitude and phase. So, as we know that the phase is bit tricky because it warps between minus pi to plus pi, right. So, the kind of unwrapping is required, but so therefore, mostly when you are dealing with the speech signals, so with respect to spectrum, we will try to mainly focus on the magnitude of the spectrum. So, therefore, here, but here if you look at this is what S of omega, E of omega, V of omega, since they are complex, it contains a real component and a phase component, the magnitude and phase. So, these are the magnitude components of S of omega, E of omega, V of omega, and this is corresponding phase like theta S of omega, theta E of omega, theta V of omega, these are the phase components and all, right. And here in the analysis of a speech, we mainly consider the magnitude component because of difficult to handle the phase component of the wrapping effect. So, therefore, we mainly focus on the magnitude part. So, that is the reason that here if you take the, and here since they are in the spectral domain, they are product. Here the S of omega is nothing but the spectrum of a speech signal is nothing but it is a product of excitation spectrum and the vocal tract spectrum. And suppose somehow if we can able to separate these two, if the components are available, if they are separable, then we can use the spectral behavior of E of omega and V of omega separately for performing various speech tasks. Suppose for example, if you want to perform a speech recognition, the goal is that we need to discriminate the sound units. That means, given a speech frame, we need to classify that as this particular speech frame corresponds to which of the sound unit, because we know that altogether there are about 40 to 50 sound units known to be phonemes, right, and we can able to classify the given speech frame as which of the phoneme corresponds to this particular speech frame. So, for that we can use the spectral information of the vocal tract and excitation separately, but here using FFT, the spectrum whatever you will get a combined spectrum, or you can say that product of these two spectra you can able to observe. Sometimes you can directly take these spectral characteristics itself for discrimination, but sometimes if you analyze the excitation part, you can able to see some discrimination information, and the vocal tract alone you can have some discrimination information. You can able to see a specific discriminative information, right. So, in that context we need to have the individual spectra. So, to get the individual spectra here, if you apply a logarithm on this the speech spectrum, you can able to see that if you apply a logarithm, and since they are product and here they become additive, right. Log S of omega is nothing but log E of omega plus log V of omega, and as I mentioned that this contains both the magnitude and phase component. So, therefore, you can able to see that log mod S of omega, it is a magnitude, log magnitude of the spectrum, speech spectrum, and this is the phase component, and here also, and with that you can able to get the log magnitude spectrum log S of omega by if you remove if you do not consider the phase component, right, the imaginary component if you do not consider, then from this expression you can able to get the log magnitude spectrum of a speech signal, that is log S of omega equals to log E of omega plus log V of omega, right. So, this you can able to see here, you can see when you perform the when you perform the FFT on this S of t. So, whatever you will get S of omega, if you take a log magnitude spectrum, you can able to see the spectrum something like this, right, that we have observed in the previous slides also, right. And whereas if you observe this can be, as I mentioned, that this is a product of both the vocal tract spectrum as well as the excitation spectrum. And since this is the spectrum corresponds to the vowel segment, it is like voiced speech segment, where the excitation is a periodic excitation. So, for a periodic excitation you can able to see, that means if you have a periodic pulse train, if you try to analyze if you try to look at the spectrum will be flat, and then in the spectrum you can able to observe the ripples. Those are corresponds to the harmonics related to the periodicity. The harmonics related to that means here the peaks, whatever the separation of peaks is corresponds to the pitch frequency. Suppose for a pitch equals, if a pitch equals to, for example, for a female speaker, the pitch is 200. It means that the vocal folds vibration rate is 200. That means 200 times the vocal folds closes and opens, right. So, it means that if you analyze the pitch harmonics, for that you can able to see the peaks are like at the intervals of 200 in the frequency domain, right. You can see the peaks, the ripples, like a successive ripple peaks. If you analyze the distance between the successive peaks will be like 200 if the pitch equals to, if the periodicity is 200. Suppose in case of a male speaker, the periodicity will be less, it may be like 80 or 90 or 100, 120, something like that. So, there if you try to analyze the excitation characteristics, you can able to see a ripple, but the ripple will be like more separated, like or will be very dense, because the pitch frequency is less, right. So, that way if you look at here, this is, so therefore, from this you can able to see this is the vocal tract part and this is your excitation part. This is excitation part. So, here in the logarithmic domain they are additive, but here separation directly from the spectral domain is difficult. You cannot do that. You can able to apply a logarithm, right. If you apply a logarithm, then you can able to see that you will see a logarithm of the speech spectrum, magnitude spectrum. Other than that you do not find. But what I am in the mathematically and analytically, you can able to see that the excitation component and the vocal tract component are separated, right. So, this you cannot see from in the spectral domain. So, therefore, what you can do here is that you can able to separate these two by taking inverse Fourier transform of the log magnitude spectrum. It means on this, if you apply the inverse Fourier transform, right, you can able to get the signal something like this. You will get the signal like this. That means whatever the S of omega, the mod S of omega, that is nothing but the magnitude spectrum, and then if you apply a log, and on this if you compute the inverse Fourier transform, you will get a signal like this, and this is known to be Capstrom, right. This is known to be Capstrom. The Capstrom is nothing but taking the inverse Fourier transform on the log magnitude spectrum. You have log magnitude spectrum, on that you are taking inverse Fourier transform. That way you will get a Capstrom over here. You will get a Capstrom, and this is known to be Capstrom. And here in this Capstrom, if you consider the first few coefficients or first few samples of a Capstrom signal, capsule signal, this is mostly contains the vocal tract related information, and then the later part corresponds to the excitation part. So, therefore, if you perform the inverse Fourier transform, you will get a Capstrom signal, right. That means you will get a sequence of values in the as a part of inverse Fourier transform, right. And here if you look at here, because suppose we perform inverse Fourier transform with the phi 12, we will get a phi 12 values. So, in this phi 12 values, if you observe the first initial values, right. So, this is corresponds to like a vocal tract information, and the rest of them corresponds to the excitation signal. Since it is a voiced segment, you can able to see in the excitation part are the samples which are away from the 0. So, you can able to see some periodicity over here. So, this is because of as the excitation is periodic, you can also see that in a capsule domain also you can see the peaks at a regular intervals, at a periodic interval, and this is your vocal tract part of a Capstrom signal, and this is the excitation part of the Capstrom signal. And for this, to prove that, if you take again a Fourier transform on this, right, you can able to see a spectrum like this, and for this if you take a Fourier transform, you can able to see a spectrum like this, and these two spectral characteristics are corresponds to one, this is corresponds to vocal tract, and this is corresponds to, so this is corresponds to the excitation, the periodic excitation and all. So that way, by performing a capstone analysis, we can able to separate the vocal tract component and the excitation component. You can separate the vocal tract component and excitation component, right. So that way, the capstone analysis of a speech will provide you the vocal tract component and excitation component separately, and with that we can able to characterize, or we can able to derive the features from this vocal tract component of the capstone, and similarly we can able to derive the features from this also. So here usually, as I mentioned that in the capstone signal, the initial part of a capstone is corresponds to the vocal tract, right. So here if you analyze the initial part of the spectrum, here usually the number of coefficients or the number of samples in this capstone as initially, where q equals to, where here the order, the number of samples will be usually, suppose the p is the linear prediction order, where as I mentioned that in case of voice to speech, the reasonable value for p will be in between 8 to 15, like let us take 12 for example. So therefore here in the capsule domain, the number of samples that will be considered will be close to 18, like 3 by 2 times, or you can say that 1.5 times of the LP order and all, the generic LP order. Suppose if the LP order equals to 15, then the number of coefficients in the capsule domain to be considered will be like 1.5 times of that, it becomes around 22, 23, something like that, right. Suppose if you consider the LP order of 8 for example, in that case the number of capsule coefficient that can be considered either 12 or 13, something like that. So that way the first 13 LP the capsule values, those are corresponds to the vocal tract system, and the rest of them can be viewed as for the excitation part. So this is for the analysis, capstone analysis for the voiced segment. Suppose if you perform the similar analysis for unvoiced segment, you can able to see in case of unvoiced segment, you can see that the capstone, the signal, capsule signal observed to be like this. You can see that initial part, this corresponds to the vocal tract information corresponds to the unvoiced segment, and the rest corresponds to the excitation part. So since in the case of unvoiced speech, the excitation is a non-periodic or a random kind of a thing, noisy kind of a thing, so you don't observe the peaks in the excitation, you don't observe the periodic peaks in the excitation, whereas in case of voiced segment you can able to see that there is a periodic peaks in the excitation, whereas in case of unvoiced signal you don't observe the peaks in the excitation signal, periodic peaks in the excitation signal. And here also you can say that initial portion corresponds to the vocal tract response, or the vocal tract properties, characteristics of the speech, and the rest of them corresponds to the excitation part. So this way one can able to like analyze the excitation component and the vocal tract component of a speech signal in a separate way, so that after separation we can use the vocal tract response or the vocal tract properties for discrimination of various things, like the speech sounds, or for discriminating the speaker characteristics, or for discriminating the language specific information. So those tasks you can able to perform in a very seamless way by using the by analyzing the capstone, or you can say that the initial samples of a capstone which are more specific towards the vocal tract system and all. And whatever the features that are derived from the capstone analysis is known to be the capsule features, and the corresponding they are known also known to be capsule coefficients and all. And from the linear prediction analysis, like whatever the LP spectrum you will get, and from that not LP spectrum, if you perform this capstone analysis like this way, and if you can able to derive the coefficients of the corresponding capsule coefficients offered by the linear prediction model, so they are known to be linear prediction capsule coefficients. They are known to be a linear prediction capsule coefficients. So, and here you can see the next part will be the whatever we are discussing will be the extraction of capsule coefficients or capsule features from the linear prediction analysis, because as you observe the linear prediction coefficients, whatever you are derived or you determined from the linear prediction analysis, So, those coefficients they represent the all pole filter. So, these coefficients are very sensitive. That means, if there is a small variation in this linear prediction coefficients, right, the roots of a polynomial will be disturbed. The roots of a polynomial will be very disturbed. That means, even though there is a small like a disturbance or the small change in the coefficients, the polynomial roots may be moved from like inside the unit circle to they will go outside the unit circle, right. So, we know that when you are discussing about the poles and zeros, like if the poles are within the unit circle or if the poles and zeros are within the unit circle, then say that the system is a minimum phase system and the system is a stable one, because if you excite the system, the system will get a stable thing, and then it will, the response will be died down in some finite amount of time, right. The system will be stable, right, if all poles and zeros are within the unit circle, right. And whereas if the poles and zeros, if any of the poles and zeros that are moved away from the unit circle, then the system becomes unstable, because that particular poles or set of poles are zeros. So, that leads to system become unstable. That means, now the system becomes from a minimum phase to it will go to the mixed phase. So, mixed phase system means there are some poles that are some poles and zeros, they are there inside the unit circle, and there are some pairs and poles of zeros, there will be some outside the unit system also. So, the poles and zeros that are outside the unit circle, so they will provide they leads to like non-minimum phase, or the phase of the system will be keep on increasing, there is no control on that. So, it is not to be non-minimum phase system and all. Whereas, the poles and zeros that are within the unit circle, so they leads to, they will try to offer the minimum phase system, and if the system contains both like pairs of some poles inside the unit circle, some poles outside the unit circle, it is known to be non-minimum phase, or you can say that mixed phase system and all. So, that is not desirable, right. So, therefore, when you are designing the system, like when you are using the LP coefficient, as far as possible the LP coefficient should be like should offer a model very stable system, so that the poles and zeros should be within the unit circle and all. But if you derive the features from these LP coefficients, for example, then the problem is that actually if there is a small change in the LP coefficient, because the LP coefficients, if you choose by since they are coefficients, we need to code that, or we need to quantize that for deriving the features and all. In the process of quantization, if there is a change in the LP coefficient, that leads to the system will become the unstable and all, will become unstable. So, that is the reason that usually the LP coefficients are used for synthesis purpose, for generating the speech, but the LP coefficients they cannot be used directly for other speech tasks, like for a speech recognition or like a speech synthesis or speech recognition or other discriminative task, right. Because the reason is because they are very sensitive, like, so that is the reason that LP coefficients cannot be used, they do not directly used for the other speech task, right. So, for that purpose, if you use the capsule analysis on the LP model or on the LP the linear prediction coefficients, so from that you can able to derive the capsule coefficients from the linear spectrum, from the linear prediction spectrum, and those capsule coefficients are more stable, they are more robust and stable. So, that way we can use the capsule coefficients derived from the linear prediction analysis, right. So, they are not to be linear prediction capsule coefficients, and they are more robust, and they can be very used effectively for discrimination of speech sounds in the context of speech recognition, and they can be used for language discrimination or speaker discrimination also. So, therefore, for performing various speech tasks or recognition purpose, basically we use the capsule coefficients or the capsule features compared to directly the spectral features and all, right. So, we will stop here at this point of a time, and we will continue the extraction of capsule features from the LP analysis in the next class.